So dilute solutions. Their pH, formality, and fraction of dissociation. That's it for me. Okay. So in a certain range of pH, we have to do a full systematic treatment of equilibrium. Otherwise, we're going to get the wrong answer. So that wouldn't be good. Let's see. And this is just really how KW is arrived at. I thought it was kind of interesting. Right? The autoprotolysis of water, that's what this is all about. Right? You have a hydrogen ion and a hydroxide. But essentially two water molecules collide. One acts as an acid, one acts as a base. So one grabs a proton, the other one accepts it. Or donates it, I guess. Grabs it and donates it. So products over reactants, but liquid doesn't show up in the equilibrium constant expression. So you just end up with hydrogen ion and hydroxide. Okay. Monoprotic acid-base equilibria. What are the 6 strong acids? Marlena, what are the 6 strong acids? HBr. HI. Perchloric acid. Nitric acid. Sulfuric acid. And hydrochloric acid. Yeah. Okay. How about the 6 strong bases, Gloriana? The 6 strong bases. NaOH. Lithium hydroxide.
Potassium hydroxide.
Good. Now the other 3 are the exceptions to the solubility rule. Hydroxides form precipitates with everything pretty much except for calcium, strontium, barium. Calcium hydroxide. Strontium hydroxide. And barium hydroxide. So there's our 6. Okay. So we have an expression for the pH. It's familiar. Ricky, do you remember at what pH is it acidic?
It's below 7.
Yeah, low pH. Pure water. You have pure water. I suppose, Melissa, we should say the temperature is 25 degrees Celsius, but what's the hydrogen ion concentration in pure water? 10 to the negative 7. And why is that? Well, it's because of this, right? Autoprotolysis of water. And that 10 negatives, okay. Hydrogen ion and hydroxide produced from water dissociation. Does hydrogen ion produced from water dissociation always equal 10 to the negative 7 molar? In other words, I don't know, and you have a can of Coca-Cola. And there's some phosphoric acid and there's some other compounds in there. It's pretty acidic. And you have water, but still mostly water. And think of it as you have a hydrogen ion concentration, and it has contributions from several species. One of them's water, one of them's phosphoric acid, one of them's carbonic acid, right? They have all these contributions, and then you end up getting this total hydrogen ion concentration. So the question I'm trying to say is, that contribution from water dissociation, is it always 10 to the negative 7? Is it always 10 to the negative 7 at 25 degrees Celsius? What do you think? Brandy says no. She's right. It's not. It's not. Let's try to illustrate that. Calculate the fraction of hydrogen ion from dissociation of water at 10 to the minus 1 molar HCl. So we have 0.1 molar HCl. So you would say that our hydrogen ion concentration is what number? What molarity? 0.01. So don't forget everything that we've learned before, right? This still works. Just realize that this has several sources. It's just HCl and water, so it only has 2 sources. One is the HCl, right? The other one's the autoprotolysis of water. But what fraction of hydrogen ion from the dissociation? So really what we're talking about is what molarity over 0.1 molar, right? That's our answer. Right? So the contribution that's from water all over the total. And how do you get that top part? You almost have to get it kind of in a roundabout way. Ida, is there any hydroxide in that solution? 0.1 molar HCl. We use the ultra pure water, man. There's no calcium in there. There's no nothing. It's just pure water and hydrochloric acid, 0.1 molar. Is there any hydroxide in there? Is there any OH? Yeah, there has to be. There's a little. Is it going to be a lot or a little bit? Jeff, is there going to be a lot or a little amount of hydroxide?
Little.
Very, very, very little, right? Extremely little. But do you agree, Jackie, that there's hydroxide in that solution? There has to be, because there's water. You can't stop it. You can't stop autoprotolysis of water. What's the source of the hydroxide? Where did the hydroxide come from, Sabina? It came from the water. So, do you agree with that, Naya? That the hydroxide came from the water, autoprotolysis? Okay. If water, Jeff, produced water autoprotolysis, produced a hydroxide. Well, doesn't it also produce a hydrogen ion?
Yeah.
Yeah. So you could say that the contribution of the hydrogen ion concentration from water is the same as the what concentration? The hydroxide. Whatever the hydroxide concentration is. Well, it's 1-to-1. It produces, right, autoprotolysis. For every hydroxide produced is a hydrogen ion. So, yeah. All we got to do is figure out what the hydroxide concentration is and say, hey, well, that's the amount of hydrogen ion that's produced from the dissociation of water, and put that number up here. So how do we get the hydroxide concentration, Kimberly? So hydroxide would be 0.1 molar? No. Anybody got an idea?
Use a KW.
Ooh, use KW expression, right? Because you know KW is what number, Desiree? 1 times 10 to the negative 14 at 25 degrees Celsius. That's hydrogen ion times hydroxide. Okay. Now these, what you just have to get kind of used to is, well, okay. Which one of these do we know? Yeah. We know hydroxide? We know hydrogen ion. We know that this hydrogen ion concentration, it is 0.1 molar. Well, I mean, that's total concentration. That is it, 0.1 molar. So let's solve for hydroxide. Let's see, that's times 10. That's what, 1 times 10 to the negative 13? Can I do stuff in my head? I think I can, right? So 1 times 10 to the negative 13 is the number that we need to put right up here. So my fraction would be, let's say 1 times 10 to the negative 12, right? Does that make sense? All I did is just divide by 0.1 or multiply by 10. So it's extremely small, the fraction of hydrogen available that's from the dissociation of water. Yeah, it's extremely, extremely small. Okay. And notice, have you noticed something already? Something in chemistry that I really kind of don't like. If we introduce sig figs, shouldn't we stick with sig figs? If we introduced what, shouldn't we stick with what? What am I getting on? Starts with an A. Activities, right? If we introduce activities to get right answers, shouldn't we be sticking with activities? they use sig figs, they meaning the community here, who write textbooks and everyone else, when it's convenient. So the book isn't using activities, so I'm not using activities. But you should always use activities. You should always use sig figs, right? Anyway, okay. When dealing with hydrogen ion concentration in the range of something to something, oh my goodness, you have to do a full treatment of equilibrium due to the dissociation of water. Does anyone know what range that is? It's pretty much 10 above and 10 below what's normal. Like what's normal is 10 to the negative 7. So 10 to the negative 6 to 10 to the negative 8. So if it's more dilute than 10 to the negative 8, it's so insignificant you don't even care anymore. But if it's in that range, oh geez, we gotta do a full systematic treatment of equilibrium. Okay. Formality. So just stop me anywhere along here if I lost you, if you have a question. Monica, why is it technically correct to refer to a solution as 0.23 formal hydrogen cyanide instead of 0.23 molar hydrogen cyanide? I mean, all the general chemistry problems, everything up to this point even, we always had big M. We never had F. And F is moles per liter. Why? What's the deal? What's wrong with that? What's wrong with saying 0.2? Because now we're all of a sudden saying 0.23 molar hydrogen cyanide is wrong. You should say 0.23 formal hydrogen cyanide. Well, if you add water, you're just diluting it, the number gets smaller. F means all its forms. Exactly why. So when you have a substance that has more than one form, and all we're looking at is really the cyanide, right? And it's getting back to the full systematic treatment. We like to write answers and solve things. Well, you've got cyanide, you've got hydrogen cyanide. And you made a bottle, you made this solution, and you want to write 0.23 molar hydrogen cyanide on it. But the cyanide that you made, it's in that solution, it's got two forms, cyanide and hydrogen cyanide. So if you say 0.23 molar hydrogen cyanide, you're saying that's exact. That cyanide in the form of hydrogen cyanide is exactly 0.23 molar. Well, what's the concentration of cyanide? I don't know, you got to calculate it, right? So no, what we should be putting on bottles and what we should be putting on everything, especially all these weak acids and weak bases, is formality. Because then we're saying hydrogen cyanide in all its forms, I don't care how complicated the chemistry, you don't even have to care about it then. And whatever's going on, there could be complex ions, there could be whatever, I don't care. I just put an F on it. So it's 0.23 molar in all its forms. That means moles per liter. So much easier. In comparison to 0.23 big M, you're saying that form is 0.23 molar in concentration. So it's much safer. So will we stick with that talk? I doubt it. I bet you give it a chapter and then we're back to writing big M. But maybe I should fix that. Just write my own book. Weak acids and their fraction of dissociation. How do you write a general Ka reaction for the acid HA? How do we do that again, Desiree? A Ka reaction. What goes to what? HA goes to H plus and my A minus. Okay. And then we had some problems where we had to find the pH for a weak acid. Oh, yeah, how do you do that? How do you find the pH for a weak acid? And HA has a solution of some known formality. How do we do that again, Kelly? We make a what table? Make an ice table. And what do we use as the initial concentration? The, not molarity, the F, the formality. All right, use the formality as the initial concentration. Okay. So I think everything seems okay. All they've done so far is just switch molarity with formality, and that we've got this little thing we have to be worried about when the concentration of some acid is in the range of 10 to the negative 6, 10 to the negative 8. We got to use full systematic treatment. But I think this is what's new, and this is what gets confusing. There's two different fractions the homework is going to be concerned with. And one is the fraction of dissociation of a weak acid. They're going to say, what's the fraction of dissociation of acetic acid? No big deal. They're talking about little alpha. And little alpha is just x over f. No, so f is what they're going to give you. That's that formality. But what's the x? Concentration. It's the what in what? It's the x in ice of the what reaction? Ka, if we're talking about weak acids. All right, so that's going to be the x in ice. It's the hydrogen ion concentration. All right, but that's the hydrogen ion concentration. That's our x. Okay, if you're talking about a weak acid. So that's one fraction that we will be concerned with, we are concerned with, is alpha, the fraction of dissociation of weak acids. Another fraction is a fraction of the total hydrogen ion concentration from dissociation of water. Kind of what we talked about earlier, right? What's the fraction of the hydrogen ion that's from the dissociation of water? And that's what we did here. Well, how do you do it? Put the total hydrogen ion concentration in the bottom, right, in the denominator, and divide that number by the hydrogen ion from the water from dissociation. And again, pretty much if you're talking about a weak acid, how do you know the hydrogen ion? Yeah, we got our X, so we have our hydrogen ion concentration. But how do you know the contribution from water dissociation? What was the trick? Get the what concentration? Danielle, get the what concentration? What was the trick? And that was your answer. Get the hydroxide concentration. The lady who got 2 hours of sleep figured this out, right? Get the hydroxide concentration, because that had to originate from water dissociation. If we're talking about the weak acids, and that's pretty much everything they're interested in here is weak acids. Okay. So I want to see if I can throw some curveballs and whatnot at you. Andy, here's the first one. What is the pH of 1 times 10 to the negative 3 formal hydrogen bromide? How would you do this?
First, we would have to write out the acid dissociation.
So write out a Ka reaction and then do ice?
Yeah. Maybe a Kw also.
HBr is on the list of strong acids. Okay, so you have to worry about something though. You want to just take what to get pH? Negative log of it. And that would be great, you'd be done. But remember, there's something you got to worry about. What was the range again?
10 to negative 6, 10 to negative 8.
10 to negative 6, 10 to negative 8. Do we have to worry about that? So just do what?
Negative log.
Negative log. And you're done. All right? Okay. Number 3. Calculate the pH of 5 times 10 to the negative 8 formal perchloric acid. Now, one thing that I am kind of confused on, to be honest with you, and maybe Marlena can straighten me out, these I got from the book. Right, they're 9-2. The author wrote these. The author says formal hydrogen bromide and formal perchloric acid. Does that make sense to you? Does it make sense to anybody? If you could explain this to me. Why am I confused?
What was the question?
Why do they have formal there? Yeah, because it's all its forms. Well, what forms are there of hydrogen bromide?
H plus would be our mind.
There isn't any. What are the forms of perchloric acid? There isn't any. It's like, okay, let's erase all the big M's and write F's. Well, it doesn't make a whole lot of sense, right? I mean, I guess, maybe what he's saying is, I mean, this is supposed to be professional guys, right? And they probably know, I'm sure they know more than I do. So maybe they're trying to send the message, never write big M. Always write F. But they're not following their own advice in later chapters, obviously. But I don't get it. To this point, I don't get it. They're just making a big deal about the importance of formality, and then to use it on something like strong acids doesn't make sense to me. So maybe someone can explain that to me someday. That's worth, I don't know, I'll give you 10 extra credit quiz points if you can answer that for me.
In the next edition, they're like, in this edition, we corrected.
So why does why does that make sense? Why is that a good practice to do? If you can answer that, oh man, I'd love to hear it. Okay, so number 3, calculate the pH of 5 times 10 to the negative 8 formal perchloric acid. Okay, same question, Gloriana. How do you go about doing this?
What's the strong acid?
Strong acid,
Negative log.
take negative log and we're done?
No. Oh no, because it's a negative 8.
It's in that stupid range. So we have to do what, Danielle? We have to do what? Full systematic treatment of equilibrium. Ah, okay. Well, you got to do it. You got to do what you got to do. We're here anyway, Ricky, right?
Yeah, why not?
Yeah, why not? Okay, so what are my ions?
H plus, ELO4 minus, OH minus.
All right. Anybody think of any others? Melissa, you think of any others? Yeah, I think you're right. Okay, how about an equation? Danielle, how about we need some equations. We have 3 unknowns. We better come up with 3 equations. Oh, the charge balance. Okay, yeah, you like that one. So H plus equals what? Yep. There's my charge balance. She grabbed the easy one. Ida, we need another equation. We have 1 down. Mass balance? Okay. That's the name of it, but what would it be? So there's how I see this for mass balance is this formality, right? That has to be the concentration of the cation, the anion in all its forms. But the story never makes sense with hydrogen ion because you have water as your solvent. So you can never talk about this being hydrogen in all its forms. It never makes sense because you have water tied in there. And water doesn't even show up in equilibrium constant expression. So you can't mess with hydrogen. So what you have to say is 5 to 10 negative 8 is perchlorate in all its forms. So how many forms are there of perchlorate? Ricky identified just 1. He was right. So we've got an equation. That's really nice and easy. Wish they were all like that. Would it be appropriate to write M or F here, Jackie? I kind of like writing M because there's only one here. If there was multiple, then it would make a lot of sense. It'd fit the definition of writing F perfect. But there's only one of them, so I'm just going to write big M. But notice how in your math it really doesn't even matter. It's kind of like saying molar mass or no, molecular weight versus formula weight. Remember, one's for molecular compounds, one's for ionic compounds. Okay. We have 2 equations, but 3 unknowns, Sabina. We need 1 more equation. KW. Okay. So what I'm going to do, equation 1 has everything in it. So what I'm going to do is I'm going to substitute 2 into 1, and then I'm going to rearrange number 3 and substitute that into 1. And then I'll just have one unknown in that equation. So I'm going to substitute 2 and 3 into 1. Substitute 2. Maybe you could rearrange 3 first. Rearrange 3 for, I don't know, for hydroxide and substitute. Or we want to get, no, this, I guess it really doesn't matter. We have to get both of them. It doesn't matter. And substitute into 1. So if we do that, we'll have hydrogen ion, all right, equals perchlorate. Perchlorate is 5 times 10 to the negative 8. And then 3, in equation 3, hydroxide is what? Well, hydroxide is going to be 1 times 10 to the negative 14 divided by hydrogen ion, right? So plus 1 times 10 to the negative 14 over hydrogen ion. So that's really the game plan in the systematic treatment, is you look for an equation that has pretty much everything in it, and then take the other equations and substitute them all into it. So that's what I did. Equation 1 has everything, so I'm just going to use the remaining equations and substitute into it. So I end up with one equation with one unknown, and I can solve for it. So what would you do first here, Naya, in solving for this thing?
So substitute equation 1.
Yeah, so in solving this expression right here, what would you do first?
Put 5 times 10 to the negative 3 is 7. Plug that into
Well, why multiply through by? I would multiply through by hydrogen ion. Right? If you multiply through by the hydrogen ion concentration, both sides, then you get it in the form of, how did it work? A, what was the quadratic formula? Oh yeah, that was the solution. The solution was this: negative b plus or minus b squared minus 4ac over 2a. But you had to get it in what form to do that? ax squared plus bx plus c. All that has to equal 0. So that's not, I was hoping I was going to say multiply through both sides by the hydrogen ion concentration, because then I can just rearrange and get it in this form.
Okay, multiply both sides.
Excellent. Okay, so I'll have hydrogen ion squared. All right, and I'm just going to bring it over right away. Minus 5 times 10 to the negative 8 hydrogen ion minus 1 times 10 to the negative 14 equals 0. So I multiplied through by hydrogen ion, and then I also just brought things over to the other side right away. So I know what my A, B, and C are. Substitute them into the quadratic expression and see what you get here. So one of those answers is going to be negatives, and that one won't make any sense. I don't know if I did that right or not. I got about 1.28 times 10 to the negative 7 for my x. The only one that's positive. Mel's shaking her head. 1.28 times 10 to the negative 7. So that's my... Kelly, did you get that? You got it? Ah, jeez. No, I don't have a calculator. You got Desiree? Okay, that's 3 people got it. That's got to be right. Okay, so that is my what concentration? That is my hydronium or hydrogen, right? That's my hydrogen ion concentration. Is that my total hydrogen? Remember, now things are getting confusing now. Jeff, is this my total hydrogen ion concentration, or is this my contribution from the dissociation of water concentration?
Total.
That's total. All these numbers are total, right? Hydrogen ion concentrations, doesn't matter what equation you pick. Right? We're talking about the total hydrogen ion concentration. It's the same number in all these expressions. That's the total hydrogen ion concentration. There's no little subscript A and little subscript B here. No, it's just, that's it. That's your answer. So we want the pH, so we just take the negative log of it. Which I don't have a calculator for anymore. No. What is it, Desiree? 6.89. Okay. Went through a lot of work, Ricky. Does that number make sense? 6.89 is a pH.
Well, let's see. It's like, yeah, that looks pretty good to me. I mean, it's very dilute.
It's a very dilute acid. So it should be close to 7, but a little bit smaller. So that's a good number. So I bet you Desiree's right. Okay. They wanted that. What else did they want? So calculate the pH. Done. What fraction of total hydrogen ion is derived from the dissociation of water? What's the trick in doing that again, Jeffrey?
The concentration of the hydroxide over.
There you
the
go.
total H+.
Get the concentration of hydroxide and put that over our hydrogen ion concentration. And that will give you the fraction of hydrogen ion from the dissociation of water. Good. Probably have to use the KW expression to get it.
Do you get like 0.6 for that? Or?
Yeah.
Simple for it.
So did anybody get a final answer? Really? 60%. Monica, what did you get for your hydroxide concentration?
7.81 times 10 to the negative 8.
Thank you. So that's what goes in here. Okay.
Is there like a symbol or something that's used to represent the fraction dissociation? Is it the little alpha thing?
No, all they have a symbol. The only symbol they have is for the fraction dissociation of weak acids. There's no symbol for the fraction of the total hydrogen ion concentration of dissociation of water. There's no symbol for that one.
Okay, so you don't put like alpha equals 0.6?
No, alpha is for designated solely for X over F.
Okay.
Totally different fraction. Okay, so backing up a little bit here. Okay, Kimberly, how do we write the chemical reaction whose equilibrium constant is Ka for benzoic acid? How would you write that reaction? This benzoic acid, C6H5CO2H. It would be what? Just take a what off of it? Take a hydrogen off it. So they're probably saying this is your acidic hydrogen, so that's what I'm going to leave. And what am I missing? A minus. Exactly. Okay. Find the pH and the fraction of dissociation of a 0.1 molar solution of a weak acid, HA, with Ka 1 times 10 to the negative 5. Right off the bat, shouldn't that M be a what? Yeah, what the heck? I wonder if that's my typo or theirs. So what's the game plan to do this, Desiree?
Can we get a negative now?
Negative, yeah, they want pH. So you're going to have to do negative log of the hydrogen ion concentration. But how do you get it? Do F. Alpha equals X over F. And that F part, everybody, is 0.1. How do you get the X? Ice. Do ice. How do you get pH? Negative log of H, or X in this case, because X is your H. Set up your ice table. Hopefully you've done that. So Kelly, did you get this far?
Yeah.
Okay. What do you do next? We're after this X.
We don't consider the X, the one, the minus X.
Yeah, consider that really, really, really small. Right? So you end up with just X squared over 0.1. I've done that before. And get your X. Substitute it in. Well, take the negative log of it. You'll have your pH, right? because X is hydrogen ion. Calculator, Kimberly. So what are you getting for your answers here? Do you get a pH or anything? 1 times 10 negative 5 times 0.1 square root for your X. So that goes there. Oh, then what's the negative log of it? That's 3, right?
Yeah, it's great.
No, that's not bad. Times that'd be 1 times 10 negative 2. Okay. Man, the fun continues. Oh, it's the last one. Man, Mal, you might get out of here early today. See if you can figure this one out without me telling you anything.
Dr. Smith, were we supposed to add the 0.1 formal to the 0.001 when you're trying to find the pH?
pH is the negative log of the hydrogen ion concentration. So the hydrogen ion concentration is just your X.
It's just that?
It's X. Because X is hydrogen ion.
Oh, okay. Okay, I see what happened. All right. Thank you.
Find the pH and concentrations of trimethylamine, ammonia, I guess, ammonium chloride. 0.06 formal solution of trimethylammonium chloride. Oh. What's that chlorine doing there? It's just chilling, but what does it do? It makes it so you can have this makes this chlorine makes this compound soluble. It makes it neutral. Makes it it could be I bet you it's a solid, right? But it's a neutral compound. So you can have that on a shelf, pull it off, and you've got yourself the conjugate acid or the conjugate base in this equilibrium. Which one? The conjugate acid. Because look at and what you got to do is just look at the rest of it. Well, I don't know. Look at this guy. There's no H there. So here's your conjugate base. So they're giving you the conjugate acid. So go back and think about every single problem where they gave you the initial concentration of the conjugate acid. You wrote a K what problem? A Ka. If this would have been, they could have just, this is nice and neutral in the first place. They could have just gave us the concentration of this one. Well, then you would have had to write a Kb reaction. Okay. But as it is, you just know the initial concentration or the formality of the conjugate acid.
Is this supposed to be like a strong electrolyte? Do you need a Ka or is it a strong electrolyte?
Man, it looks like we're going to have to Google it.
That's
Because is this a strong acid? It's not on our list of 6 strong, so that means you have to Google this guy and get a Ka. Now maybe I have my notes and I can give it to you.
It might be like K or Na where it dissociates readily.
Let's see. Man, nobody brings their book to class, right? There's no reason to. 1.58 times 10 to the negative 10. I got to add that. 1.58 times 10 to the negative 10.
Not very.
Maybe I didn't give it to you because, times 10 to the negative 10, because I wanted you to practice looking it up in the table. Ka. That's the Ka. Ka. Do we have to do a full systematic treatment? No. The contribution isn't going to be big enough. Only in that range of 10⁻⁶ to 10⁻⁸ molar, weak acid, weak base, strong acid concentration. Anybody get an answer for this?
I got an answer now.
I don't know either. 5.5?
Yeah, for the pH. And then I got 3.
5.5.
8 times 10
And oh, and concentrations. So both of those will be X, right? And what did you get for your X?
3.08 times 10 to the -6.
3.08 times 10 to the -6. So if you got those numbers, you're free to go.
How do you get? Oh, I see. I was like, why did you from them? Okay. Yeah.
Oh, yeah.
Oh, hold it. NH plus. So they're both not the same. NH plus is that minus X. 0.06 minus X, isn't it? So Mel, what's that one? Since I don't have a calculator.
5.9 times 10 to the -2.
Thank you. Okay. So have a good day.